Do a research proposal and then like 500 words.
Okay, I think we're ready to get going. One more coming in, but we're basically ready. Okay. All right, today I want to talk about some details of linear systems, which might seem like a strange thing to do in a nonlinear systems course. But as we talked about before, we want to develop kind of a foundation. We want to look at how nonlinear things compare to linear things because we know mostly about the linear systems. So that gives us kind of a point of departure, basis for going on and looking at the new things. This is going to be a really quick review of linear systems, kind of in the context and using some of the terminology we're going to use for nonlinear systems. So it's kind of a way of starting down that nonlinear path in a particular direction that we want to follow. Okay, we've talked about superposition before. That was our basic tool for understanding when a system's linear and when it's not. So if we take a general system in the state space form, and if it turns out that is linear, then as we saw before, we can, through a linearization process, it would come out in this form. So we can talk either about the linearization of a nonlinear system, or if the system is actually not linear to start with, then it will come out to be in this form exactly. Okay. So if we take that basic differential equation, one of the very nice things about that is that we know what the answers, the solutions to that thing look like. Okay, we can write them down in closed form, and no matter how complicated A and B are, we're able to do that, right? So there's no guessing about what the solution would be. So that's one of the first and perhaps foremost niceties about linear systems is we can write down these solutions directly. And the way to see how to get that is actually, if we just use an integrating factor, that is this e to the matrix AT thing. So if we multiply that by both sides of this differential equation, then it turns out we can directly integrate it. That's what the integrating factor does for us. Does anybody remember what the c to the AT object is?
Matrix exponential?
Okay, that's what it's called, but what is it, really?
Like the series expansion of it, or?
Yeah, whenever you see e to the AT, that's a symbol meaning a series. That's what e to the AT actually is.
Is that only for time invariant systems, or is that for?
You can have time varying A matrices, okay? And because of the strong convergence properties of this power series, right, you have the same series expansion even in the time varying case. It turns out in the time varying case, though, you can't necessarily integrate this equation. So if you go away from time invariant, then once again the solutions to the differential equation become non-obvious, right? You can't always just write them down. So this is linear and time invariant case, really. Okay, so this e to the AT is a compact expression for this crazy series. It's a matrix infinite series. Okay. But it turns out, there's a lot of stuff you can do with this to show that this thing acts just like you would think of as a scalar exponential function. even though it isn't anything like that, it's this weird series, it has all these same sort of properties. So if you differentiate this thing with respect to t, you get the expected thing where the a minus a comes down in front, like you would have with an exponential function. And that, isn't obvious from this form, but if you take this series form, you can prove those kind of properties. Okay? So that's why, this thing here is used a lot, even though itself doesn't really mean anything. It's the series that's really what's going on there. So anyway, we can take that, and we can write down the solution for x of t. Here it is. Okay? What would we call this part of the solution?
A natural response.
That's natural response. What else would we call it?
Transient response.
Homogeneous.
Not always transient. What else would we call it?
Homogeneous response.
Yeah, we could call it the homogeneous response. The one I'm looking for is initial condition response. Okay, so if we had just initial conditions and no input u, okay, we would have this as the response of the system. And if we have no input u here, we have a homogeneous differential equation with no external influence. So that's where the homogeneous response comes from. What would we call this part?
Input response.
Sorry?
Input.
Yeah, logically, but I've really never heard that term, so it's not really called the input response.
Forced.
It's not entirely the forced response either. It turns out the natural response is determined by this e to the at thing, right? And so there's an e to the at inside here. So it turns out this thing always has two parts to it. There's always a forced part of it that has a character that looks like u, and there's always a natural part of it that has this character e to the at that comes from the differential equation, from the system. Okay? This is often called the zero initial condition response, because the initial conditions are zero. We don't have this term over here at all. We just have this term. You can also think of this as the input-output response. In other words, with no initial conditions going on, the output is strictly a function of the input according to this convolution operator. So this is a convolution of the input u of t with the impulse response e to the a t e. Okay, so the point is we can write down this thing, even though it might get complicated. It's a closed form thing, we can write it down. Okay? And because we can do that, we already know a lot about what the response looks like. Okay? And a lot of this comes from, the properties of this impulse response e to the at. And some will come from the input as well, obviously. The character of the input will influence this term anyway. Okay? But there's a lot we can tell about the response of the system from that e to the at formulation. And one thing that's pretty obvious here is that this system satisfies superposition, right? Because if I stick in, for u, if I stick in u1 plus u2, since the integral is a linear operator, multiplication by this matrix infinite series is a linear operator. I could split this integral into two terms, one involving u1, one involving u2, right? And then the integral involving u1 would be the response of the system to u1. Call that y1, say. This produces y1 of t. The input u2 would give us another output y2 of t. And then I could add the two outputs together and get the same thing as adding the inputs together and putting it through this formulation. So we can see easily now, because of the linearity of this operator that we could write down for the closed form solution, we obviously have a superposition property holding. Okay. What about superposition with respect to the initial conditions?
Matrix multiplication is also a linear operator.
Exactly. We get the same deal. This is a linear operator here. We can split it into two terms. And the response due to the one plus the response due to the other is the same as the response due to the sum. Okay, so it pretty clearly satisfies superposition. Okay, and I mentioned, since we have this particular form e to the at, I can write down, I already know a lot about the responses, just knowing something about A. Now, A can get big and can get complicated, so the easiest way to see what really is going on here is to transform the system into a form where A is as simple as possible. Okay? So let's consider saying that, let's replace x of t with some matrix transformation to another state, call it v of t. This is a similarity transformation. If t inverse exists, so in other words, if t is non-singular, this is a similarity transformation. And really it's just saying, I had some description of the state space here, this vector x, and I'm just really changing coordinates in the state space. Okay, so I'm not changing the system itself, I'm just changing the way I measure its behavior. I change the way I measure the state as a function of time. Okay, that's all t is really is a coordinate change. Okay, but if we pick a special coordinate change, if t is such that t inverse at is diagonal, then it turns out the elements on the diagonal are these lambda I of A, the eigenvalues of A. Nice thing about doing that is now if I go back in and replace x of t with tv, so there's a couple ways to do this. If I go back to the differential equation and replace it here, so x dot is tv dot because t is a constant matrix, it's not changing with time. Then I have tv dot is a tv, and since t is non-singular, I can invert it on the left on both sides to get v dot is t inverse a tv. And we said now that t was special because now this is diagonal. Okay, so what has that done? Well, it's decoupled the states in the state space because now, v1 affects v1 dot, but v1 dot is not affected by any of the other v's because this is a diagonal matrix. Okay, so it's decoupled these states completely in the state space. Huh. Looks like something has crashed. Just trying to get my pen to work here. Come on. Okay. Let's try it the other way. So, in other words, if I look at just these individual elements, vi, of the vector v, that's going to be lambda I vi. Okay? And now the solution to that scalar differential equation is the simple exponential solution, e to lambda I t. So, vi of t is e to lambda I t vi of 0. Okay, so in this simplified form, in these new coordinates, the states are all independent, right? And they evolve really simply according to this simple exponential function form. Okay? Now, this is the simplest when lambda is a real number. Okay? And, you know, then we easily see what's going on here. If lambda is a positive real number, what do the solutions look like?
Exponential growth.
Yeah, they blow up over time, right? They get bigger. If lambda is a negative real number, then they decrease over time. They exponentially converge to 0. Okay? So that's pretty simple. What happens if lambda are complex? Well, then I get complex vectors here, complex, you know, coordinates here in the state space. So you can do that. You can decouple this, you know, as long as this thing diagonalizes. Those diagonal elements, some of them might be complex, if the eigenvalues of the A matrix happen to be complex. So you can still do that, but then you get complex signals here, which is kind of disconcerting, except that those eigenvalues always come in conjugate pairs. And so it turns out these solutions, these VI coordinate things, also come in conjugate pairs. Okay? And if you take the pairs together, they always annihilate the imaginary part to make a real signal. Okay? So if you're willing to look at the complex stuff here, you can keep it in this really simple form, the scalar differential equation form. However, most people like to think of real modes, and so they like to look at the case when these solutions here are real signals directly. Okay? Okay, so before I go on to that, this thing here is called J, which is called the Jordan form of our original matrix A. So in the case when we can diagonalize the A matrix, the Jordan form is a diagonal matrix. And that's the simplest possible case, right? Can we always do that? Can we always diagonalize?
From an engineering point of view, you can.
Yeah, so turns out if A is what's called semi-simple, then J is this diagonal form. Semi-simple is not quite as simple as simple. Simple is the case when the eigenvalues are all real. and I can diagonalize it with a real t, and always get real modes here, exponential modes. It's semi-simple if I can still diagonalize, but then maybe some of the eigenvalues are complex. Okay, so that's why it's not quite as simple as semi-simple, but still, it's pretty simple. Okay, so that's where the terminology it comes from. If A is not semi-simple, then the Jordan form, I'll just do an example here of it. It's kind of tedious to write down the general form of it, but it would look something like this, say. If I had repeated eigenvalues lambda 2, I would get like a super 1 here instead of a diagonal matrix. So this would be diagonal except for this guy here. So it turns out that I can sometimes diagonalize the A matrix even though I have repeated eigenvalues. And that would be the case when I get a diagonal form here with a 0 here instead of a 1. And that would be semi-simple. Okay? The non-semi-simple case has these super diagonal 1s that show up. And that's where we need generalized eigenvectors, and we get this more complicated kind of stuff. Okay? And so in that case, the solutions don't look like this anymore. We can get solutions here where vi of t have things that look like t to the n e to the lambda I t. Okay, so different kinds of solutions that are non-exponential strictly. Okay. Now, this gets back to the interesting thing that Aaron just brought up is, you know, how often does this occur? Okay. And so it turns out these non-semi-simple cases here, these are what's called not or non-generic. In other words, they don't, these forms here, these Jordan forms that are non-diagonal, don't hold up under perturbations. So if I go into the A matrix and make little adjustments to the coefficients, generally I can make this thing, if it was non-semi-simple, I can make it semi-simple with arbitrarily small perturbations. Okay? So non-generic here means that it's not robust to perturbations. So this gets back to your point about engineering. If we have a model for this that comes from some engineering system that's an approximation to reality in some way, right? Well, there's nothing there that prevents me from going in and making arbitrarily small changes to that approximate model and not really changing the degree of my approximation, right? It's already an approximation. If I go make arbitrarily small changes, well, it's still as good approximation as it was before, okay? So I'm free to sort of perturb and not really change the engineering situation, okay? And so if I happen to do a model that had one of these more complicated Jordan forms, I could go in and perturb things a little bit and get a regular diagonal Jordan form, a semi-simple case, without really changing the degree of my approximation, practically. So there's nothing stopping me from doing that. So really, these non-semi-simple forms, I don't really ever have to deal with, because I'm free to go in and perturb slightly and get something that's simpler. So from an engineering perspective, what you said is exactly right. We don't really ever have to worry about these non-generic cases. So the case of a diagonal A matrix and the semi-simple A is what is the generic form of a linear system. Okay. In almost every case of interest, that's what you get. Now, the only cases that you don't get that is if you're trying to do something mathematical and you're trying to be rigorous about it. Well, then there are cases, right, that you maybe can't perturb because you're trying to be totally rigorous about it. And then you have to deal with the complexity that results from that. Okay. Okay, so that's the picture with the homogeneous solutions. Generically, they separate into these diagonal forms where you have individual modes, and they're exponential in form here for the solutions for each of those individual modes. So really, what we want to know is not so much what is the A matrix, but what are the eigenvalues of A, because those are what determine those solutions and what they look like. Okay? And we can directly see a lot from this. If lambda I, say, had a real part plus sigma plus an imaginary part omega, right? Then we could write e to the lambda I t as e to the sigma I t times e to the j omega I t. Okay. Now this is a real exponential. It decays or grows based on the sign of sigma, the sign of the real part. What does this guy look like?
Sine, cosine.
Yeah, if I use the Euler theorem on an imaginary exponential, this thing looks like cosine omega t plus j sine omega t. So it only oscillates. And it oscillates with frequency omega here. Okay, so if I know the eigenvalues, I already know almost everything there is to know about the solutions here. The thing I don't really know is how big are they, and that's a function of this initial value, this initial condition in the state space. Okay, but I already know whether they decay or grow based on the real part of the eigenvalue. I know if they oscillate, what frequency they oscillate at based on the imaginary part, omega, of that eigenvalue. Okay, so just looking at the eigenvalues, we already know a whole lot about what the solutions will look like. And of course, this is why this is so useful for design, because we often have an idea of what we want the system to behave like. We know how fast we want these solutions to decay. Typically, we want them to decay so the system is stable, not blow up, right? And if we have oscillations, we may have an idea of what kind of oscillations we're willing to allow. So we already have an idea of what the solutions ought to look like. In other words, what the eigenvalues of the closed loop A matrix, when we're done with our control, what that should look like. Okay? So then if we start with an eigenvalue that's not what we want, we have an idea of what we want. The question then is, how do we change the eigenvalues from what we started with to what we want? And that control design problem then really comes down to choosing eigenvalues with your control design. Okay? And then there are a bunch of techniques that we've already seen how to do that. So a pretty straightforward approach to understand what the system is and what I want it to be and how to get from there one to the other. How to control the system to behave as desired. Okay, the other main point of view here and this is, from the non-state space point of view, this is from the input-output point of view. So we don't really think of the system having a state space or an internal state necessarily, but we think of it as an input U and output Y. And we have this nice idea that if I put in a sine wave for U, as a function of time, suppose it's sine omega t, so a unit amplitude sine wave with no phase shift, then it turns out we have a pretty clear idea of what to expect on the output here. Anybody want to take a crack at what the output looks like here in general?
Sinusoid of the same frequency with a phase and amplitude change.
Maybe, sort of. What else is missing from what you just said?
Oh, some kind of a natural response.
There's always the natural response. And if the natural response is stable and decays to zero, then you'll be left with the forced response, which is that sine wave that you mentioned. Right? So generally you have some transients going on here, and then this thing will settle down to a sine wave. Okay, so the steady state part of this is something that looks like this. A sine omega t plus phi. Okay, and it turns out tell you what, let me not use A, because we've been using A for the state matrix. So to avoid as much confusion as possible, let's call that G. Okay. Where it turns out generally, as a function of frequency omega, G here will change with frequency. Okay? And the same thing with this phase shift phi. Phi is a frequency-dependent function. Okay? So we know G and phi together is the frequency response. It's how the system amplifies sine waves and how it phase shifts sine waves at various frequencies. Okay, and that's the frequency response. The thing to not forget, though, is that we only have the situation where the transients, the natural responses, those e to the at things we just talked about before, those only decay to zero under certain conditions on the system. And what are those conditions?
All the eigenvalues have negative real parts?
Yes, exactly. All the eigenvalues have negative real parts. So this only decays to zero when lambda I of A real parts are strictly less than zero, all of them. Okay? As we just saw before, that's when we have these exponential decay envelopes on whatever oscillations might be there. It's only when we have that this transient term is going to decay to zero, leaving this forced response as the only output. Okay, so the really nice thing about linear systems is that, modulo this transient stuff, sine waves in give you sine waves out at the same frequency, with an amplitude and phase shift that turns out to be an easy thing to calculate. So if this thing had a transfer function h of s in there, from a Laplace transform point of view, then it turns out G is the magnitude of h evaluated at the frequency of excitation. And it turns out phi is the angle of this complex number h of j omega as a function of frequency. Okay, so if we have the transfer function here, it's straightforward to compute the magnitude and the phase of that frequency response, that transfer function, at each frequency, and you can get these curves, G and phi, like this. So you have this sort of big picture view for all possible input frequencies. How does the system behave? Okay, and this is something that's very unusual, for most systems. Only for linear systems can we get such a comprehensive view of how all frequencies affect it, with just simple plots like this simple frequency response plot. So again, this was used, for great insight and great advantage for design purposes, because again, often we have some idea of what these functions ought to look like to satisfy our objective. So for example, if we have a system like this h of s, and we wrap a control loop around it, and we want that control loop to track a reference trajectory accurately, right? What would I want the closed loop transfer function here to look like? So it wouldn't be, h anymore, the plan, it would be the closed loop transfer function. To get good tracking, we would want this frequency response magnitude to look like 1, say, over a large frequency range, which would mean the output looks just like the input, the reference input. Okay. So we have a good idea of what to expect, what we want there, and the question then here is how to just modify the transfer function to have those frequency response qualities that we like. Okay. And again, there's a bunch of Bode plot, Nyquist plot kind of tools there to help us design that transfer function or that frequency response to be what we want. Okay. Let's look at linear systems from some of the terminology we'll be using for nonlinear systems. So, equilibria. An equilibrium call it X star. Is a particular solution to the differential equation. And it's one for which the rate of change of the state, the time rate of change, is 0. So if we think of, a general sort of state space here, this is our value here for some x, generally f of x, which is x dot here, right? That's the rate of change over time that you have beginning at that point. So that you think of that as a little vector sticking out here, right? That's the direction you're moving. Okay, so an equilibrium means what?
You don't move.
You're not moving. Equilibrium is a place in the state space such that when you operate on it with the, the function f of x, you get no motion. So you're not moving from that point. So the differential equation solution starting there is to stay there. Okay? So it's a stationary point in this differential equation. Okay? Suppose then that x dot is f of x, which is linear. So we know that's going to look like this. Okay? What kinds of equilibria can linear systems have? What's the obvious equilibrium for this system?
0.
X equals 0, because a times 0 is always 0. Right? So obviously, x equals 0 is always an equilibrium for a linear system. The origin of the state space is always an equilibrium for a linear system. Are there any others? Are there any other ways that x dot could be 0 here? Yes?
Right null space. Anything in the right null space of A.
That's right. Any x in the right null space of A produces ax equals 0. That's what the right null space means, right? In fact, that encompasses the first one we just solved, right? 0 is always an element of the right null space. Okay? So, x in the right null space of A is an equilibrium, which includes 0. Are there any others?
So if you assume A is 0, if you don't look at the trivial case, or if you look at the trivial case.
Well, even if A is 0, it has a right null space.
Right. Everything's right.
Okay. So, suppose there was some x that wasn't in the right null space, such that ax equals 0. Does such a thing exist?
Yeah, isn't that the definition of the right null space?
Yeah. It violates the definition of the right null space. So there are no other solutions. There are no other equilibria. Okay. Everything in the right null space is an equilibrium, and only things in the right null space are equilibrium. Okay? Okay? So again, it's pretty easy to figure out what the equilibria are for a linear system. We just look at the right null space of A. Okay? Now if A is really big, that might not be easy to see, on pencil and paper, but you can throw it on MATLAB and you can look at the right null space. Okay. What if A has non-zero eigenvalues? What is the right null space of A?
All non-zero eigenvalues.
Sorry?
If it has all non-zero eigenvalues.
That's right.
Then just 0.
Right. Then we only have the trivial solution here for the right null space. So the right null space there is a 0 dimension. There's just one point in it, 0. So if all the eigenvalues of A are not at the origin, okay, in the complex plane, then we already know there's only one equilibrium at the origin. That's it. No other equilibrium anywhere else in the state space. Okay. When A has 0 eigenvalues, then we know the right null space will be non-trivial, so we know there'll be more eigenvalues. How many more?
Infinite.
Yeah.
Well, because everything in the right null space. So the subspace of A, right, has infinite numbers of points in it. Okay, it might have dimension 1 or dimension 2 or dimension 3, but even at dimension 1, it has an infinite number of points on that line. Okay, and so those, like the right null space in that case, might be some line, for example. And because it's a subspace of the domain of the A matrix, right, it must go through the origin. Okay. So we have this entire line of equilibria in that case that go out to infinity, right? If the right null space of A is two-dimensional, then we have this sort of plane going through the origin in the state space. And again, it stretches to infinity in all directions. Okay, because it must be a subspace. Okay, so equilibria for linear systems are pretty easy to figure out, and they follow these simple rules. There aren't that many things that can happen here. Equilibria are either points at the origin, and that's it, or there are these subspaces of lines or planes, hyperplanes, right, going through the origin as equilibrium. So in particular, there are no isolated equilibria. Right? We can't have an equilibrium hanging out here all by itself. Because if it is an equilibrium, it's got to be part of the subspace, the right null space of A, for example. And so it must be included in this entire line going through the origin. So we cannot have isolated equilibria in linear systems. Okay, so the equilibria are either at the origin, or they're all together on these subspaces, lines and planes and so forth through the origin. Okay, what about periodic orbits? So periodic orbit is a solution x of t such that that same solution at some later time, cap t, equals the solution at a previous time. And so there must be some fixed cap t for which this is true, and then this has to be true for all time. Okay, so if I slide t along, there's some delay cap t for which the values of that solution are the same. Okay. So if we look at one of these things as a function of time, just in the scalar case, here's one, 0, which is kind of a trivial periodic solution, right? The value is the same for all time, so it would be the same for any cap t we do this for. Okay. You can also do for other constant solutions, right? Those are periodic. They're sort of trivial. Okay. The one we think of most often is some kind of oscillation, right? With period cap t. When can we get a periodic orbit in a linear system? Yep.
When the real part of the eigenvalue is 0 and then imaginary part's non-zero?
Right, if you include my trivial cases, the imaginary part could be 0. Okay, but you can only get this, either of these things with constant solutions or oscillating solutions when the real part is equal to 0. Okay, so these imply that the real part of some eigenvalue equals 0. And generally, you're not going to get a truly periodic solution unless you start with just the right initial conditions. And so particularly if we look at the, the similarity transformation that decouples everything, right? We could look at the initial conditions such that we have initial energy in this mode, but none of the other modes that might be decaying or growing. Okay? So in that case, we just have energy in this mode. It starts it off in the right initial condition, and it just oscillates there with no decay or growth. That's the really only way you can get this periodic solution, but it is a solution to the differential equation for a particular initial condition. Okay? So if we were to look in the state space, this kind of periodic solution, obviously the equilibrium at the origin, that's one such solution like that, right? It's periodic, but it's kind of the trivial one. This oscillation generally would take a shape like this. So again, a closed orbit in the state space. So if I started somewhere on here, cap t time later, I'm going to come back to the same point to satisfy this condition here. And I stay on this orbit for all time, right? Just oscillating around on that orbit. Okay? So there are no equilibria on that orbit, because there's no place on that orbit that if I start there, I stay there. Okay? But in some sense, that orbit is a constrained place in the state space. Okay, it's a very tightly constrained thing. I'm on this very narrow track, and if I start on there, I stay on there forever. Okay, so this is one of the things it's called an invariant set. Okay. That if I start on that set, I stay on that set forever. Okay, so periodic orbits are a type of invariant set. Okay. Now, what's going to be of interest when we get into the nonlinear stuff especially is if I start just at any old point in the state space, the question often comes up, do I ever end up in a desirable place? Do I ever end up there? Right? So if I started here and somehow found myself being attracted to or pulled into this kind of periodic orbit eventually, okay, then that invariant set is sort of the place I end up. Right? I end up somewhere in that invariant set, and in fact, in this case, as time goes to infinity, I end up being captured totally by that invariant set. Okay. So one of the ways to describe these places you end up are what are called limit sets. So there are two kinds. An omega limit set and an alpha limit set. And these are essentially the places you end up. In the omega case, they're the places you end up if you take time backwards in the alpha case. Okay, which would seem like a bizarre thing to do because we all think of time as always going forward. But with differential equations, right, you can do what you want with time. And we'll see later there's a good reason for thinking about running time backwards. But for now, you normally think about the omega limit set, and that's the place we end up. Okay. So what that is, we first have to look at what an omega limit point is. And that's some point P such that x of t sub I converges to P for this sequence Ti going to infinity. So Ti is a sequence of time points. Okay, and it doesn't say it has to be regular sampled time points, but just time points that end up at infinity. Okay, so a point P is an omega limit point if the solution to the state space system converges to P as these time sequences go to infinity. Okay? So for example, let's look at this sine wave here. If we said, I want to know if this point P right here is an omega limit point, the question would be, does this solution x of t converge to P for time samples here such that the number of those samples goes to infinity?
So if you can choose the time samples you take, yeah.
Yeah, so here we could say, well, okay, here's a point where that x equals P. Here's another point where that x equals P. And so I can identify an infinite number of points here that x equals P. So it certainly satisfies this definition here for an omega limit point. Okay? However, a P up here does not. There are no points that satisfy x converges to P there. Okay. What if I have a situation like this where I started somewhere but I end up converging to this periodic solution? So maybe I start up here somewhere, right, and I end up getting closer and closer to this periodic solution over time. Okay. Once again, in that case, I could identify points P that actually equal it, and it satisfies this case, right? So the thing about the omega limit set is it allows us to identify where we end up. Oop. Come back. Without having to, one more time, without having to identify that final solution. Okay. Okay, so every point P that satisfies this, x gets close to P. I guess another way, a little informal way to say this is that P is visited infinitely often. There's another sort of informal definition for what a limit point is. It's a point that the solution visits infinitely often. Okay. And my even more informal definition is, where do we end up?
Does it have to be an oscillation? Because like an exponential decay will in theory never get to that point.
Okay, well, let's examine that. So if we said we have this exponential decay that comes down to 0 over time, and let's ask the question, is this point P a limit point of that system? No, because after this time here, that solution is bounded away from P, so it certainly doesn't converge to P. In fact, there's only one point here, it looks like, that x would equal P. So it fails that condition. But what about P equals 0 here? Well, there may be no points that x actually equals P here, if it really is just a limiting process. Okay? But I could go on and make these samples, and the value of P at those samples would then have a limit of P, and that satisfies the definition for a limit point. So the thing we converge to here, even though we never actually get there, is the limit point for the process. Okay, so that's a good example, good question. Thank you. Okay, so it turns out the omega limit set for a linear system is either an equilibrium, like we just said, like this case of 0, if everything is converging to 0, you know 0 is an equilibrium, or it's a periodic orbit. Okay? It turns out we can't ever get these kind of things for a linear system that start off somewhere and converge to a periodic orbit. You either start on the orbit and stay on it forever, or you start off the orbit and you never get there. Okay? And the reason we know that is because we know the solutions to the ODE are either things that are completely periodic, sines and cosines, or they're sines and cosines that have exponential envelopes on them, in which case you never stay on that orbit. You either decrease to 0, you fall off the orbit and go to 0, or you fall off the orbit and you blow up. You never stay on the orbit unless the real parts of those eigenvalues are 0, in which case the only way to get on the orbit is to start on the orbit, in which case you stay on it. Okay, so pretty simple situation. And again, we don't have these kind of converging to a periodic orbit situations at all for a linear system. So let's look at what's called these hyperbolic cases. So a hyperbolic equilibrium is such that there's several different cases here. So let me do maybe the easiest case here first. If the real part of the eigenvalues of A are all negative, what is the omega limit set? So what do all the solutions do?
Go to 0.
They all converge to 0. So what is the omega limit set?
Just the 0.
Just the origin. Just the origin. And there's no other points that get visited infinitely often. Just the origin. Any other point in the state space, the state might come by you, but it's going to pass you and go to the origin, and so it's going to go away from you over time. Okay? What if the real part of the eigenvalues of A are always positive? What is the omega limit set? So first of all, what do the solutions do?
They blow up.
Yeah, go to infinity.
They blow up.
They all blow up.
So it's empty set then?
So is there a p-value that I would visit infinitely often if the solutions blow up? No.
Would you have an alpha limit set though in that case, or?
Yeah, so here's how we think of alpha limit sets. If I take time backwards, what do all those solutions do in this case? They converge to the origin, right? Because we have an e to the positive number t. If t is negative, all those things converge to 0. So here we have no omega limit set. It's empty, right? But we do have an alpha limit set. And that is, again, the origin. Okay, what if some of the eigenvalues of A are positive? So the i's are positive and the j indexes here are negative real parts. What do the solutions do?
Still grow exponentially.
Well, some will, but not all. If I start in the subspace corresponding to these eigenvalues, I stay in that subspace, and that decoupled form tells me that I have exponential convergence to the origin, right? So if I start in that subspace, actually I converge to 0. And so I'm going to have omega limit points at the origin there. Okay? But if I start in other places beyond, away from those subspaces, then those solutions would blow up. And there'll be no alpha or no omega limit points associated with those, only alpha limit points. Okay. So we would have p equals 0 as both an alpha and omega limit set. And once again, we know that because in that decoupled form, these solutions look like that, and this lambda here either has positive or negative eigenvalues, so this thing is either expanding or decreasing, okay? And so the only way you can have limit points is if you have, 0 as the limit point as you're decaying to 0, or if you go backwards in time as you're decaying to 0. Yes?
So in this case, it depends on where the initial conditions, what eigenspace they're in?
Well, if we're asking what are the entire limit sets, the things you can get for every possible initial condition, where can you end up from any possible initial condition? That's what the limit sets tell us. Well, that includes all those special initial conditions, right? So again, there are some initial conditions for which we have an omega limit set. And there are other initial conditions for which we have an alpha limit set, right? And so the whole picture of where we can end up going forward in time or backward in time, in this case here, is one point as a limit set. Because we're including all possible initial conditions in that question of what are the limit sets. Okay, let's contrast that with what's called a center equilibrium. And that's the case where the real part of one of these eigenvalues equals 0. Not all of them necessarily, but if there's one of them that has a 0 real part, what is the omega limit set? So what do the solutions look like? Yes?
It depends on the initial condition.
Okay, go ahead.
I mean,
Go on.
the omega limits, if the imaginary part is 0, then it's just the initial condition. And if the imaginary part is non-zero, then it's any number between plus and minus your initial condition.
So what's complicating issues here is, there's other eigenvalues perhaps that aren't this, right? So if I start in the subspace determined by these eigenvalues, so-called eigenspace, okay, then we know the solutions, again, evolve according to this. So if I start in the right subspace with that initial condition, I get this simple behavior. I stay in that subspace. Okay, those are invariant sets, those subspaces. And I evolve according to this thing here. And now what you're saying is, in the case where lambda is 0, both real and imaginary parts are 0, then wherever I started, I stay there. I don't move. So that's an equilibrium, right? On the other hand, if the imaginary parts are non-zero, then I know I get oscillation here. So I get these periodic orbits. Okay. So if all I know is the real part is 0, and I don't know anything about the imaginary part, generally I would say then the omega limit sets can be either equilibria or these periodic orbits. And once again, if I start on that orbit, I stay on that orbit, right? So these either could be equilibria, so 0 is always there. There may be others if the right null space of A is non-trivial. also periodic orbits. And this would be true if the, the imaginary part of lambda I is not 0. Then you get periodic orbits. Well, I should say non-trivial periodic orbits. Right? The constant solution is technically a periodic orbit, but it's kind of trivial. And so these here would be the case where lambda I equals 0. So, either we're going to be stuck on some equilibrium, either at the origin or some entire subspace when the right null space is non-trivial, or we're going to be stuck on some periodic solution. So if I get on one of these, I stay on them forever. Okay? So that's true for the particular eigenvalue here that might have had a 0 real part. But what about with the other eigenvalues here in the rest of the system? What do those do? I mean, these solutions here only occur when we start in the right subspaces, when we start with those precise initial conditions for that case. But if we start out with an initial condition that has components in other directions where these subspaces corresponding to the eigenvalues have eigenvalues of non-zero real parts, you can swallow all that, what happens? What do the solutions look like?
They're either going to be growing or decaying, depending on.
Right, because those don't have real parts of 0, so they're growing or decaying. So, in other dimensions here, maybe out of the paper or out of the board here, you might have something growing or decaying. Okay, but in the plane here corresponding to the center eigenvalues, you have this kind of limit set behavior. So, for example, if we started out with a case when one of these other eigenvalues had a negative real part, then I would decay down to this motion in this plane. Okay? I wouldn't necessarily be starting on this orbit. I'd be starting off the orbit, sort of out of the paper. But then I know that eigenvalue is negative real part, so I'm decaying down to this orbit in the paper. Okay? So, let me attempt to draw this. The trouble is, this gets into higher dimensions, and it's really hard to draw these things. But if we take this plane here, so this is the eigenspace associated with real part of lambda I equals 0. And so in this plane, we know we get these periodic orbits, say. So in this case, example here, I'm presuming, I guess, that the imaginary part of lambda I is not 0, so I get these oscillating orbits, okay, instead of just equilibria. And then suppose I have another eigenspace sticking out here, E2, we'll call this E1. Doesn't have to be orthogonal to that plane. This eigenspace here might be associated with a case where real part, say, of lambda j is -1. Okay? So now, if I start up, and let's suppose these things are going this way. If I start out up here, what happens? Well, I could break this initial condition here down into a component in the eigenspace E2 plus a component in the eigenspace E1. And then I know those components now. When I look at this decoupled form, those components are going to evolve simply because they start out in their own eigenspaces, right? So this component does what?
Moves down towards the origin.
It converges to the origin because this is the negative real part. Okay? This component does what?
Oscillates.
Right, it stays on its closed orbit that it started on. Okay, so what does the aggregate behavior look like when I look at those two components according to how they evolve? What would I have here?
Spiral down to the orbit. Right?
Yeah, I don't think I would call it a spiral because it does not go to the origin. The radius doesn't increase. It's a cylinder, really. So I have this oscillation on this cylinder that's going to end up down on this closed orbit. Okay? So that's what's nice about this decomposition into the different eigenspaces, is that I know what the behavior on each eigenspace is. That's pretty simple. Then any initial condition I can always write as components in all the different eigenspaces. And then I know how the components evolve, so I could add those back up to how the initial state evolves. Okay? So conceptually, that's very straightforward. It's kind of tough to draw in a good way, especially when you're talking about more than 3 dimensions here. But conceptually, that's not complicated. We just have this split into all these different eigenspaces, and we know what the behavior is on each eigenspace. Okay, so we can conceptually, understand what the overall behavior should be, pretty simply. Okay, so we're going to come back later to the reason that we split these two things into separate pieces. I guess one obvious reason here is in the hyperbolic case, the limit sets are really simple. There's just one point in the limit set. In the center equilibrium case, the limit sets can be more complicated. They can be these lines or they can be these closed orbits. Okay. But we'll come back to that stuff later. Okay. Let me take about a minute here and finish up this idea. It's we sort of already were just talking about it. So these eigenspaces we said are subspaces. So again, this is the state space. There's only 2 components here just so I can draw it. X1 and X2. This might be the eigenspace E1 associated with lambda 1. And we might have another eigenspace here, E2, associated with lambda 2. And so again, any initial state I might pick here, X, I can write as a component in the X2 direction plus a component in the E1 direction. Okay. And then I know how these components of the initial conditions evolve, knowing the eigenvalues. Okay. So here, just to kind of do another case here, suppose lambda 1 here was equal to minus 1, but lambda 2 is equal to 2. Starting at this initial state, what happens?
The E1 component dies off, but the E2 component grows exponentially.
Right.
So it looks like a triangle towards the E2 eigenspace. A curved line.
So I move like that. Okay? This component goes away. This component gets bigger. Okay? What about if I start over here?
You'd kind of be going down towards, yeah.
Okay, over here.
Up again towards.
Yep. And then down in here.
Towards E1 and then away from E2.
Do something like that. Okay, so this is an example of what's called a saddle equilibria here. If I start on this narrow line here, anywhere on this line exactly, I end up at the origin. But if I start anywhere else in the state space, even just infinitesimally off that line, here. Okay, I'm going to end up going like that to infinity. Okay, so again, it's pretty easy to figure out what's going on here by splitting up into subspaces. Behavior on the subspaces is simple. Okay, and the point about these manifolds is since these are subspaces, they're flat. They're scale invariant. Which basically means that if V is an element of this subspace E1, then necessarily alpha V is in the same subspace for all scalars alpha. Okay, and this, you recognize this from the vector space subspace formalism, right? This fact that you have scalar multiplication, this set is closed under scalar multiplication. It makes it a subspace. So these things are flat. They extend to infinity. Okay, which is something we generally don't have in nonlinear systems. Often these manifolds corresponding to these simple behaviors can be warped and bent. They may not go to infinity. They may terminate on other equilibria, and strange kind of things can happen. Okay? Yes?
How come both of the lines starting at the origin are going out?
Well, these manifolds are subspaces, right? So they're lines that go through the origin. Now, motion on them depends on the eigenvalue associated with the eigenspace. So in here, we're going in.
Okay, yeah.
We're moving in. Right? This was just the initial component that adds up to x here. This isn't moving out here.
Okay.
Right? That's just the initial component. Its rate of change is negative, so it's going in. This one is getting bigger. Okay, any questions? Okay, next time I want to finish up the discussion of linear systems with kind of a really detailed idea of two-dimensional phase plane behavior and talking about all the different kinds of behavior and giving them names that we'll be using later. And that'll be the basis then for talking about all the interesting stuff that we can do with a nonlinear system. So we'll finish that up on Thursday. Okay, see you then.